Welcome to the HKS Energy Policy Seminar. I'm Joe Aldi. I'll serve as the host for the seminar today. As a reminder, we're running the seminar in hybrid format. So thanks to those who are joining us by Zoom. Thanks to everybody joining us here in the room, and for our colleagues and for our fellows and students, you're welcome to join us here in the Elwood Democracy Lab at noon on Mondays in person for the seminar. We're thrilled to have with us today a colleague from the faculty here at the Harvard Kennedy School, Professor David Keith. David is Professor of Applied Physics at the School of Engineering and Applied Sciences and Professor of Public Policy here at the Kennedy School. He's worked near the interface between climate science, energy technology, and public policy for 25 years. He took first prize in Canada's National Physics Prize exam, won MIT's Prize for Excellence in Experimental Physics, and is one of Time Magazine's Heroes of the Environment. He's the founder of Carbon Engineering, a company developing technology to capture carbon dioxide from ambient air to make carbon neutral hydrocarbon fuels. And David led the development of Harvard's Solar Geoengineering Research Program, a Harvard-wide interfaculty research initiative. David is here today to give his talk towards quantitative comparison of the risk and benefits of solar geoengineering. David, welcome back to the seminar.
Thank you very much. Great to be here. That one. Now I am. I apologize for that. Sorry to Zoom land that I wasn't turned on. Next time, just feel free to stand up and shout if I'm doing this wrong. So the way I think about it is there are four fundamental ways to break this causal chain between economic activity and climate damages. The first is decarbonizing the energy economy. That's the one thing I think we can say we must do. I think you really can say we must do it. I think the policy debate is about how quickly we do it. And I won't really get into that debate much, except just to say as a sort of framing, although there's lots of sense right now in the climate activist community about despair because we won't meet 1.5. For somebody who's actually been, the intro said 25 years, I think it's actually about 30 years since I started working on this now. I actually see lots of optimism in the terms of faster action on emissions reduction, both politically in terms of sensible policy and in terms of the technological change. Most importantly, having really cheap solar power has just been a stunning and I think unexpected change. So then carbon removal. And carbon removal is getting a lot of attention right now, maybe even a little over attention, in my opinion. I think it's really worth dividing into two very different things that often are lumped together, but really are almost completely distinct buckets. One are all the ways we might increase carbon stocks in the biosphere, in trees or soils or what have you. And the other are ways that we might really engineer permanent removals that essentially reverse the thing that causes climate change, which is taking carbon from the geosphere, from deep underground, and putting it in the atmosphere. And so those are adding alkalinity to the ocean or capturing CO2 from the atmosphere and putting it underground by direct air capture or biomass capture. That is not a case of one of those good and one of them bad. Things involving trees and soils are generally cheaper, but they're more inherently short term. They can have co-benefits or co-disbenefits. I just think they're really different, and thinking about them in one lump isn't very helpful. As I said, I think there's a little overexcitement about carbon removal right now, and it's partly because it in some ways seems easier to some people than cutting emissions, and I think that's mostly because we haven't really begun to look hard at what the political and cost trade-offs are involved in doing it at scale, basically who pays. And we have looked hard at who pays for emissions cuts, and it's clear it's hard, and I think carbon removal can look like a kind of shiny techno object that's a fix because we're not thinking enough about the fact that a lot of the same or different versions of the hard trade-offs about who pays are still there. But having said that negative thing, I'll say one sort of personal thing. So I was involved or was the founder of this company, Carbon Engineering, and after 12 years since we founded, or 13 or something now, it actually gives you a sense of how slow these things are. But CE actually, a company is now starting construction of a 1 million ton a year plant. So a full kind of order of magnitude bigger than the next biggest plant. And that's now real. The sense that construction's actually started as kind of $1 billion class capital commitment. And that really is to me, exciting sense that things are moving, although obviously I have a self-interest in how to think about this. So then the main topic here is solar geoengineering, and I'll say a little bit more about what that is. And then finally, adaptation. And I think a way to think about it is if carbon removal breaks the link between historical emissions and future climate change, because as I hope you all know, bringing emissions to zero doesn't solve the climate problem. It just stops the climate problem getting worse, stops it getting incrementally worse. Carbon removal really can reverse that by reducing the underlying driver of climate change, the carbon in the atmosphere, but it is inherently, in my view, a slow thing to do. Solar geoengineering doesn't break the link, but it may weaken the link between the amount of carbon in the atmosphere and the amount of climate change, but it introduces new risks as well. And adaptation also doesn't break the link, but it weakens the link between climate change and impacts to people or ecosystems. So here's a little cartoon of what some of the methods are of solar geoengineering, and I'm happy to answer detailed questions, but just to say that for me, the set is quite big. Different people define the set differently, and as is common with any disputed technology, people have different names for this. So solar radiation modification is the IPCC's kind of standard right now, but other people want to call it solar climate intervention, range of different names. But to me, they all deal with this basket of things that ranges from quite, I think, science fiction things, certainly science fiction in the next half century, that we could build a shield in between the Earth and the space. People have worked on this for decades, but I don't think could happen soon, to the thing that we've studied the most, which is putting aerosols, fine particles in the upper atmosphere, sort of twice as high as a regular aircraft flies, to ways that we might manipulate thin cirrus clouds in ways that are actually quite similar to the way that contrails from aircraft act, and a set of other ideas for how we might make a certain kind of marine low-level cloud that you find in, say, off the west coast of the US a little lighter. So there's a range of these. I won't say more about them technically, but happy to get interrupted with some questions, and I'll pause for questions a few times. But now to kind of the core of what I'm trying to do here. So in the discussion in the policy community concerned with this, there are lots of calls for the idea that we need quantitative risk to risk comparisons. And this is, I think, one nice example of a really good quality recent report that makes this call very strongly. And it provides a great deal of structure to what a risk-risk comparison might do, but it doesn't really provide any numbers. So I think this is a terrific report, and we're thinking about who wrote it and how it came to be. This Carnegie Climate Governance Initiative is this entity founded by Janos Pastor, who was formerly the chief advisor to climate to Ban Ki-moon, so kind of at the center of the global climate negotiation process. And it's an effort that's trying to advance governance of these technologies without taking a position about whether they should ultimately be used or not, but just that international governance is important. And this provides a nice framework for kind of waving the flag that we really need quantitative comparisons, but it doesn't actually provide the comparisons. And here's one table from that report, and I'll happy to take one question there. Just shout loud, I think. Yep. So the list of things would have been, so the question was, if that the question was that I showed those 5 different categories of solar geoengineering, and the question was, how much different would that have been 5 years ago or 10 years ago? The answer is that list would have been exactly the same. So a bunch of those things have been thought about for decades. We know incrementally more about some of them. I'll come back to that at the end, but there's no big change in what we know. I think this idea is getting more traction, and there's certainly more traction in conversation, not necessarily in what we do. And there's certainly more research than there was. But it's important to say this isn't like some new invention. These are old ideas, in some cases more than a half a century old ideas or a quarter century old ideas that are really about applying a set of things we sort of know in atmospheric science, aerosols, aerospace engineering to an applied problem. So this gives you some sense of again, from that paper I just showed you, from the Felgenhauser et al. Paper that C2G published, of the kinds of comparisons you might care about. So this is talking about the target would be climate risks, and this is about the risks and benefits of adding SRM, solar radiation modification, to a portfolio that already includes emissions cuts and carbon removal. And then you can think about a set of benefits. So reducing temperature, reducing changes in humidity or whatever. And then you can think a bunch of risks, and then you can think of co-benefits and countervailing risks. I won't go into the details. Their paper has pages and pages of this with a really nice set of references. What I'm going to do is in one particular one, give you something that's quantitative. But first, I'm going to try and say be a little less abstract about what kind of thing we might be talking about. So I'm going to focus on this idea of putting aerosols in the stratosphere, thinking particularly about sulfur aerosols, and just give you a few numbers and a little picture, and then I'll come back to my risk-to-risk comparison. So you have something a little more quantitative, and I'll pause just before I start the risk-to-risk. So if one wanted to cool the planet of order a degree C or half a degree C with this 2 watts per square meter of radiative forcing, where that roughly offsets doubled CO2 in terms of total radiative forcing, what physically needs to be done, what physically would accomplish that, is to put something like 1.5 million tons per year of sulfur in the stratosphere using high-altitude aircraft. So this kind of summarizes something about that. And when you just see that, if you haven't thought about any comparisons, you might easily think it's completely insane to put 1.5 million tons of sulfuric or sulfur. So that's actually more like 3 times that for sulfuric acid into the stratosphere. But and it may be insane in some respects, but comparisons are really relevant. So the Pinatubo volcano, which was the last volcano that put substantial sulfur in the stratosphere. Volcanoes that put sulfur in the stratosphere can cool the climate, in some cases a lot. Some historical volcanoes really drastically cooled the climate. The Pinatubo volcano in 1991 put 8 million tons of sulfur in a single eruption. And there's some really good examples of the fact that the science, even at the time, it's always easy in science to correctly predict something after it happened. It's much more challenging to do it before it happened. And there was at least one paper that predicted some of the key temperature response to Pinatubo that was published before you could see the response. That gives you some confidence that even in 91, we had reasonably well-calibrated models that told us something about this. And we had pretty good models about how it would affect the ozone layer. And so that's 8 million ton pulse in 1 year. And I'm talking about 1.5 million tons a year. That doesn't say it's all okay to put 1.5 million tons a year, but it says that we have some real empirical basis to know something about what the risk might be. I think that's a really important thing to say. This isn't some completely theoretical thing. And the other one to say is that the global current emissions of sulfur into the lower atmosphere, which is quite a different thing, which causes air pollution, is of order 50 million tons a year and going down actually pretty quickly as we have better air pollution controls. Indeed, that number is probably out of date. Then you can see some similar comparisons here. So just, I know this is an atmospheric science class, but roughly the atmosphere that we all live in, which turns over roughly every week, is in the lower part of the atmosphere, and it's separated from the stratosphere, which feels very different. Things in the stratosphere move with about a 1 or 2 year time scale. They move in a way kind of like smoke does in a slow-moving, smoke-filled room. It's really quite different from the atmosphere we live in. And the altitude of the stratosphere depends on where you are, but in the tropics, you need to get to about 20 kilometers, which is twice as high as a regular aircraft flies, just to give you a sense of that. So I'll say something about what the response would be. So this is an example of a particular climate model. Any climate model has benefits and is good or bad compared to other climate models in various ways. This is a very high-resolution climate model that is particularly good on tropical cyclones and on variability of tropical precipitation. But on the other hand, this particular version uses an extremely simple model for solar geoengineering. It just turns down the sun, which is not the same as anything you could directly do except for the space-based shields. And what we were looking at here was using some very standard metrics to understand how uneven the response to solar geoengineering, or to this simple proxy for solar geoengineering might be. So one of the things that's been said for a long time is that yes, solar geoengineering could reduce global average temperature, but that doesn't mean it necessarily is reducing climate risks very much, because climate risks are fundamentally the sum of local climate changes. And local climate changes, not just of temperature, but of precip, of water availability, of extreme temperature, and so on. And you might reduce the global average, but make things much worse off. I mean, if you reduce the global average by making one hemisphere a lot hotter and one much, much colder, that would make everybody a lot worse off. So just the fact that you've reduced the global average doesn't necessarily say you've reduced risks. What matters is local. And many people, including me, writing 20 years ago, said, well, yeah, solar geoengineering might be useful for a global average, but it really won't work very well because it will really be very unequal. And this is one example of many now that show that in climate models, it is possible for solar geoengineering to be much more equal than we might have guessed. So what we do here is we look at 4 of what I think it's fair to say are the most important physical climate hazards at the surface: average temperature, extreme temperatures like the hottest hour of a year, precipitation minus evaporation, which is the amount of water availability, the runoff, if you like, and then extreme precip, that's the 5-day extreme precip, which drives flood risk. So those are really important measures of risk. And then for each of those, we've coded them towards whether they're moderated, means that solar geoengineering tend to push them back towards pre-industrial, and exacerbated means is tend to push them away from pre-industrial. And more or less, you can think of moderated as being good and exacerbated as being bad. But as you'll see in a minute, that is a value judgment that might depend on who you were and what the variable was. But if you take a purely kind of ecocentric point of view, then I think you could say moderate equals good and exacerbate equals bad. And so this shows you the coding, and we coded them for statistical significance. And in this particular model, there were no variables that were statistically significantly exacerbated, which is kind of stunning and feels too good to be true. I don't think it is true in the real world. It's unlikely to be true. But it still really shows you this really different answer than what a lot of us expected 10 years ago, which is that solar geoengineering would really necessarily have big inequalities. To be clear, there are versions of solar geoengineering that, if done unequally, would have big inequalities. This is showing that that doesn't need to be true. I'll show one more slide and then come to that question. So this is a different model, a model that I'll also show you again later. That's the Geoengineering Large Ensemble from NCAR. This doesn't use this crude just adjust the solar constant. It actually has a sulfur cycle in the stratosphere. It's got quite sophisticated stratospheric dynamics, but it's got other weaknesses. This model, we did exactly the same analysis method. And here you can see that there are a few places where P minus E is exacerbated. But this gets to this, is it better or worse? So in fact, all the 4 regions where it's exacerbated, it gets moister, and they're all pretty dry regions. So my guess is for humans in those regions, they would actually think that that was better, but for desert tortoises in Chile, you'd think it was worse. Yep. Yep.
Steady state predictions. So my question is, these are predictions, but are these steady state predictions? Because if we're thinking about local effects, we're thinking about weather, maybe. And so if the sulfur we put up stays up for a year or 2 years or something, comes down, would we see these effects in that time frame, or would it come over 10 years of doing
all the stuff I'm showing is for a slow moving, roughly steady state. The first, the slide before this actually is for something that really was a 200-year steady state average. The slide that is behind me now is for the Glenn's result, which is a continuously varying simulation, but then we've done an ensemble simulation.
Do you have a guess for how long we would have to do this sulfur experiment to see the steady state effect?
There's no, it depends on how big an area you're measuring the signal to noise. I can send me an email or some good papers on that. To be clear, if we're doing this, this is not an experiment, this is implementation. So now I'll say a little bit about, so I said a little bit about some of the benefits, if you like. I'll give you a little bit of structured benefits and risks, and then take a pause for some questions before I plunge into the main quantitative thing in this talk. So there are a whole bunch of concerns one might have about these technologies. This is from a paper I published in Science last fall. That was my attempt to provide a taxonomy for what those concerns look like. This is not unique. You could divide these other up. People are taking pictures, but these things are all complete, feel free, but these are available online. Just go get them. Totally. Yeah, no problem, no problem. But this is all available online, and you can, just to say, like, this paper is freely available. All my papers are available on my website. I break copyright, so you can just download them all. So just no reason to do this. So this is my version of this, and I'll go back and forth between 2 slides. This is the one from the actual paper. This is a simpler version. But the way I see it, there's a set of things that are physical risks of deployment that was done with good intention. It was done benevolently. That doesn't mean it was omniscient. You can do things benevolently and still make mistakes. You can have all sorts of unintended effects. So there's a whole series of things that can go wrong, even if the intention was broadly to achieve some kind of utilitarian benefit for the world. And so a lot of what we've been talking about so far are all things under there, but that's got to also include accidents and incompetence. And you've got to think about an engineering system and the ways that accidents can happen. I think this community really hasn't done enough of that. So that gives you some sort of top level. And then there's a set of concerns that I would call justice or injustice concerns. And I think you can divide them into a couple. One are pretty obvious: procedural and distributive justice. So who gets to make the decision about altering the global climate this way, a procedural question. And then independent of whoever gets to make the decision, there's the questions of what is the actual distribution of harms and benefits and distributive justice. And then there's this thing that's often called moral hazard, which you can conceive of in lots of different ways, but I actually do think it is usefully conceived of as a kind of injustice. And there's really 2 kinds. One is a political exploitation kind, where if the parts of the society that want to oppose emissions cuts, like the fossil fuel industry, exaggerates or somehow politically exaggerates the effectiveness of solar geoengineering as a tool to avoid emissions cuts. That's a kind of political exploitation of a small group against the interests of a larger group. But also you can imagine a kind of collective addiction effect that has nothing to do with that, but has to do with the fact that maybe our society is just too easy to take these kind of short-term fix against a short-term fix with problems, short-term band-aid against a kind of long-term risk reduction. Then there's issues of conflict. My first thing was about physical risk, but a benevolent deployment, but you can imagine people attempting to use these technologies in ways that was not benevolent. I think some of us have now thought about this quite a bit, and I don't think we've answered all questions, but I think these problems look less big than you might think. These technologies, most of the ones I've showed you, just don't work well for malevolent use, but that's not to say there's no problem. And then there's a bunch of issues around humanity and nature. So I just want to flag that, because now I'm going to go to something that's much more kind of narrow, but I want to flag that there's a broad set of concerns. So any questions about what I have so far? Yep. And feel free to shout out and I'll repeat if you like.
Yeah, just wondering, so I know the model was just looking at max and average temperatures, but I was wondering, is there any insights into how this would affect sort of other measures of temperature that we're interested in? So length of the growing season, non-linear temperature effects, heating and cooling degree days, these sorts of things, just because if it would reduce variation, that might also be obviously a very important aspect to it.
Yeah, those are all good questions. There's some of those things where there's explicit papers, other ones where you could download the data and look at it. There are now, I don't know, of order 10 papers that looked at agricultural impacts. I don't know of any paper that's really looked at degree days. And we did a side calculation in one paper about how this might affect cooling loads, but it was really a side calculation. So those are all fair questions. So this is the core of what new that I want to present. So if you injected sulfur to cool 1 degree C, which I'm just taking as a kind of benchmark, this is all kind of linear, so it wouldn't really matter if I'd done this all at half a degree C or a tenth of a degree C. But if you're going to do that, then you can think of a whole list of harms. So maybe this will affect the visual appearance of the sky. Maybe it will kill people by air pollution mortality. After all, we're introducing something that we know is a pollutant that kills people, so we should obviously think about that. There are different ways it may do that. Maybe it'll make local climate change worse. And then there's a bunch of ways it might make things better. And that list is just partial. So what I'm going to focus on from this talk is just these 3, basically because I have data for them, but I'll defend at the end that there's a reason to believe these are pretty significant. And so this is not a kind of totally random collection, but this is where I said towards a quantitative comparison. This is absolutely not a quantitative comparison. So the next little section of my talk will be really going through a way to actually calculate some mortality estimates for all these three and then compare them. So I'm going to start with the lower ones, the harms, and that really is built on one particular paper, although there's now a bunch of other papers that do somewhat similar things. And that one particular paper looked at the harms in health outcomes from putting these aerosols in the stratosphere. And actually some background to that paper I think is important, because any new research, you got to ask who did it and do you trust them? Because it's actually pretty easy just to get papers published and why people have the expertise. So the way this thing got done is it was Steve Barrett's group at MIT. He's one of perhaps the world leaders or a world leader on estimating the health impacts of global aviation. And they have chemical transport models called Geoengineering, or a special version of Geoengineering, and they have all the health epidemiology models, and they were already tuned up to do that, to calculate impacts of emitting pollutants from high-flying aircraft. And so I teamed up with that group to do the same thing for putting sulfur in the stratosphere, which turns out to be a pretty similar problem. So we're kind of adapting that existing set of tools to this new problem. And when we thought about this, we thought mostly about this direct black line, because that seemed like the obvious one. If you're putting 1 million tons here in the stratosphere, you're going to have particulate matter coming down to the ground, and you got to worry about that because it's we know that particulate matter from sulfur on the ground causes harm. But this is a case where I think we actually learned a lot in doing the modeling of things that weren't obvious, because there are a bunch of other effects. Of course, if you put this sulfur in the stratosphere, you're cooling the climate, and cooling the climate turns out to change all sorts of atmospheric chemistry. So it changes the amount of particulate matter or surface ozone for given human emissions, because there's some nonlinearities in atmospheric chemistry. And we hadn't really thought about that much beforehand. And there's this UV flux. So I won't go into all the details of this. I'm just going to give you the numbers. And I'll give you one other slide to give you a sense of how complex it was beforehand. But here are the numbers for this 1 degree C. Air pollution mortality, and there's some issues about how to do it, goes up by of order 7,000 a year. And the putting the sulfur in the stratosphere further exacerbates the loss of ozone, which increases surface UV, which kills people from increased UV, and that's sort of 4,000 a year. Those are, I've given you just point numbers, just to make the slide simple. We actually did that with uncertainty ranges. We propagated uncertainty from all these different variables that we selected in ranges and propagated them through. This is in that original paper. And there's all sorts of complexity here that I won't say much about, where the actual thing we're looking at here, which is this direct aerosol impact of the descending mass. That's the thing we started with, that puts sulfur in the stratosphere, it comes down and hurts people. That turns out to be quite small compared to some of these indirect warming offset issues, which I'm mostly ignoring here because they'd be sort of the same if you were almost the same if you're cooling the world by having less CO2 in the air. So I'm just going to, for now, take those numbers, but don't believe that this is 7.400. This is a quite uncertain thing that I think you should believe. I would believe that it's sort of order 10 to the 4 is the way I read this, not that it's 7.4 10 to the 3. But on the fact that it's an order 10 to the 4, I think you can say that with some confidence, because there's other papers that say that in different ways. And again, because this isn't some totally new piece of science, it's adapting some well-established methodology for understanding the health risks. So then I'm going to talk about some stuff on new work that Tony Harding, who's in the audience, a postdoc of mine, is doing in a collaboration where we're really applying some of the latest epidemiological estimates of temperature-related mortality to the solar geoengineering problem with some new simulations. So we're using this temperature mortality relationship from Carlton et al., but Tony and I, or Tony, it's always easy to say for the professor to say, and I have actually looked at several of the other specifications pretty carefully as well. But this gives you some sense of what's under these things. So what these do is for each city, they look at how, or each region, they look at how mortality varies with temperature, and there's basically a minimum mortality temperature. And then if it's colder than that temperature, or if it's hotter than that temperature, mortality goes up. And it goes up on both sides. So if you're right at the minimum temperature, making you cooler increases mortality, or making you warmer increases mortality. There's also ways you can account for adaptation, technological adaptation, which is done in these papers. Happy to say more about that. But essentially what we're adapting is this particular one from Carlton. No, this is from Michael Greenstone and collaborators, which seems to be one of the best of these things, but all of them have strengths and weaknesses. And we've really adapted all the coefficients from Greenstone et al. Then we used a climate model that's a particular choice. We wanted to use, again, a high resolution climate model because these high resolution models probably do a better job in the tails of the distribution of extremes. And there's reason to believe that extremes matter quite a lot for these mortality estimates, which is why we chose that. But there's weaknesses to this model as well. I won't say much about it, except to say that in this analysis, we are more and more thinking about a ratio measure, where it's obvious that solar geoengineering cools the climate. Even the strongest opponents of thinking about it agree that. The issue is about how it does it differently or from the way CO2, having less CO2 would cool the climate. So we think it's often most effective to look at this as when you're looking at some climate effect. In this case, it's the hottest 10% of daily minimum temperatures. When you're looking at some climate effect, to look at the ratio of that climate effect if you cool the world 1C with solar geoengineering to the same effect if you cool the world 1C with a less CO2 in the atmosphere. And so that's that ratio we're looking at. So in this case, the areas that are blue are areas where solar geoengineering is a little bit more effective than reduced CO2 in reducing this 10% of the daily minimum temps, and red is the opposite. So then we take the epidemiology and the climate model, and we combine them, and we produce an estimate for the population-weighted change in mortality. This is mortality in deaths per 100,000 per year. This is all for this 1 degree C change. Actually, let me just finish a few more things, and I'm happy to take questions on this. I'll finish 2 more slides. And so if you haven't thought about these mortality numbers, you may be sort of unanchored to them, but let's give you some comparisons. So just the global annual rate given people's life expectancy is like, just the rate that people die is like 800 per 100,000 per year. And COVID at that peak was around 100, to give you a sense of these numbers. What you see here, obviously, is that if we're talking about the impact of cooling the climate down, not very surprisingly, we actually increase mortality in places that are very cold, because in cold places, cold-related mortality tends to dominate. And if you make it more cold, you increase mortality. And in hot places, you do the opposite. This isn't weighted by population density. I mean, this map is not weighted by population density. We have separate maps that can show you they're weighted. The population-weighted average here is 13. And if you take 13 per 100,000 and multiply it by 9 billion people, you get about 1.2 million a year, just to give you a sense of that comparison. I'm going to say something else about heat attributable mortality, but now I'm happy to take the question.
Tails.
Yeah.
And being, sorry, something about the tails being very important to look at.
Yeah.
Sorry, this is very basic, but why is the tail? Because usually we say the tails are. I'm in basic quant class.
Yep.
So I still have training wheels on. So what does right? What does usually we don't look at the tails because it's so extreme. So why do we look at the tail on this one?
So for temperature-related mortality, there is at least, well, there's a common assumption out there that temperature-related mortality is really dominated by the few hottest days. It's certainly true that when we really kind of count bodies, so I lived a lot of time in Alberta, and last year, right a few miles from British Columbia, the British Columbia coroner says that we're roughly more than 500 deaths in British Columbia during that heat event. And that's a kind of formal coroner estimate of a peak. And so those estimates tend to focus on these really small number of hottest days. Different of these econometric studies of temperature-related mortality actually have different weightings for how much the tails matter. So the one, and this is where I'm going to point to Tony, is going to do it better than me, but the green study at all uses an impulse function, but the impulse function actually smooths out the very sharp temperature variation. Some of the others see it more. I think the answer is we don't know well enough how much the total matters, so we want to use a model that did a good job of having the tails. That's maybe my summary, but I think it's actually not clear how much those peaks dominate the overall mortality. And I'm not an expert. I want to say one other thing. Almost all these papers, and I find this really surprising, but this is where I'm not an econometrician. Almost all the papers, and there's lots of papers now on heat-related mortality, just look at temperature. And yet we have lots of reasons to believe physiologically that wet bulb temperature, that's this combination of temperature and humidity, ought to matter more. That is, that being at 30 degrees C at 80% RH is really tough. and being at 30 degrees C at 40% RH is a nice day. And yet almost none of the epi papers use that. And as well as wet bulb, there's also wet globe temperature, which takes into account how sunny it is and how windy it is, which obviously ought to matter. There are a particular way to do that calculation. And so, so almost all econometric measurements just use temperature. There's a strong basis to believe that wet bulb or wet globe would be a better predictor of how humans actually feel heat. If relative humidity and these other factors are very tightly correlated with temperature, if that relationship was always the same, then it's reasonable to just use temperature as the index variable and ignore all that stuff, which is effectively what the epidemiologic literature has mostly done. But solar geoengineering will change the relationship between peak temperatures and RH or insolation a little bit. And so you might expect that results would differ. And so maybe you shouldn't trust the results I've showed you because we've used those relationships. Does it matter? So I don't think we've answered that question completely. We haven't done the epidemiology because doing that again is really hard. I think it really is worth doing the epidemiology seriously in a way that takes account of wet bulb or wet globe. What we did is just look at, for annual mean heat waves or cold waves, look at these same ratio number I showed you before and look at the population weighted ratios for just plain temperature, which is sort of what I showed you before. So this is saying that solar geoengineering is 9% better than reducing CO2 in just 9% better, it's more or less the same in changing peak temperatures. But then this is the same calculation for wet bulb and for wet globe with the confidence intervals, and it doesn't make much difference, which suggests that there's not a big error we're committing here. But I think broadly that especially in places like Indonesia with very high relative humidities, I think we do need these functions to actually pay attention to wet bulb. So I showed you the results for this one model, and again, I'm showing you results now for a different model, which is this NCAR, same NCAR large ensemble I showed you before. This one does have temperatures evolving over time, so this shows you the change in deaths per 100,000 per year, and here I can get a very large number. I think not incredibly large number. If you scale here to like 200 and you multiply by 9 billion, then you get 18 million deaths per year averted. But this is in this, I think, really extreme case of RCP 8.5 brought back to pre-industrial, which I think is not a very realistic case. But anyway, if I take the case that I have so far, now I've got my number of 1.1 10 to the 6th per year, and I can make a comparison. And the comparison is sort of order 100 to 1. That's the kind of core new thing I wanted to say. Do I believe that number is 100 to 1? No, I could easily make it 10 to 1, but it's very hard to make it 1 to 1. And while some of this is new work, it rests on a lot of work which has actually been done a lot of times before. Now, I've just chosen these particular values. There's lots of other things I didn't look at. There are lots of other benefits and harms that aren't here, but this is, I said this paper was about towards a quantitative comparison. This is the beginning of quantitative comparison. And these are not small things. There are lots of, quite a few different papers that suggest that of order half or more of the total sort of utilitarian utilitarian or monetized impact of climate change on humanity is heat related. So in choosing that as a benefit, I'm choosing a big one. And in terms of sort of paper citations or visibility, this issue of impact on ozone or impact through particulate matter as a harm of solar geoengineering is a pretty salient impact and a pretty obvious impact. So we chose something that's pretty important, but there's lots of things we didn't look at in either direction. Maybe I'll take a few questions about this, and then I have a few kind of wrap-up slides, do something else. Yep.
Thanks. I found it super interesting how for the benefits part, you made sure to compare to what it would do if you were going to reduce 1 degree of warming using CO2 reductions. Do you do the same thing for the harms? My sense was that you're not including the harms or benefits that would be incurred by reducing greenhouse gas CO2 emissions that way?
You mean in this this weird atmospheric chemistry? No, we didn't. And I think we're still disputing which is the right version to use in the paper. So this is this. I mean, all these numbers are still relatively small in order of magnitude, but this is this stuff that I really glossed over, which I'm trying to think of what is partly like kind of almost an ethical question. What's the right way to think about it? So these are these quite large effects that if you just cool the climate down and you leave the same source emissions of NOx and VOCs, and I don't know how much air pollution chemistry you know, if you have the same NOx and VOCs is what regulators actually regulate. And ground level ozone or PM is what actually hurts people, but those are not one-to-one related. It depends on temperature and other things. So what we find in this particular model, but this is where there's a lot of uncertainties, and the way this model did it was kind of a hack. In this particular model, cooling the world down decreases ground level ozone quite a lot and increases ground level PM quite a lot. And I'm not sure how we should count them. All these numbers are still comparatively small compared to 1 million, right? These are still these sort of 60,000-ish numbers. But I'm not sure what's the right comparison. I think Tony, I'm kind of going to struggle with that. Tony's sitting beside you. Yep.
Professor, what we see is that the benefits
Yep.
that solar geoengineering would bring.
Yep.
So my question is that what I see is that the benefits that the solar geoengineering would bring to health are transitory, whereas the damage done to the ozone layer is permanent. So how do you balance between these two?
That's true for some things. I think that's a good question. I mean, well, a central question, the sort of a big version of your question is that how to think about these things over time. But no, actually, the ozone would also be transitory. So the underlying thing that damages ozone is the chlorine that we put there with CFCs. And if you have more sulfate aerosols for the year or so that you have them, it makes the CFCs more effective in destroying ozone. But that would snap back after a year or two when the sulfate went away. So it's not permanent. And indeed, I think the whole ozone thing is kind of overblown if you're thinking late in the century, because we do have the Montreal Protocol. Chlorine is going away. And if anything, we may have a problem of what atmospheric scientists call super recovery. We actually have too high ozone late in the century. So it's a high visibility thing, but it's actually pretty small in terms of impact.
Thank you.
Yep.
Thank you for this. In terms of the same comparison that we were talking about earlier, which is comparing solar geoengineering to actually reduced carbon in the atmosphere. I know you alluded to this earlier in a question that was asked, but assuming that we can kind of overcome some of the challenges with the moral hazard, distributive justice, etc., and implement tomorrow. What are we talking about in terms of timelines of implementing, and then also timelines of actually realizing the benefits? Because
So I mean, maybe what I should say more bluntly is, I mean, to be, if it was equal cost and difficulty to reduce CO2 or do solar geoengineering, at least from my perspective, is completely clear cut that you should just reduce CO2 in the atmosphere. Even if there are some obscure ways in which solar geoengineering might be more effective at some things, it's completely clear cut. But the issue is, of course, that you can't just compare them. That reducing CO2 in the atmosphere, the only way to do that involves stopping putting it in and doing carbon removal. And those things at the scale we're talking about, which is trillion-dollar class scale, have themselves big impacts, and they work slowly over time. So that's where you really have this hard decision over time, where solar geoengineering could reduce risks, but it doesn't deal with the underlying problem, which is the CO2 in the atmosphere. And so I sort of haven't said this yet in this talk, but I think my view is that the best you can say about solar geoengineering is a combination of emissions cuts and carbon removal plus solar geoengineering might have, if we use good policy, less risk than just emissions cuts plus carbon removal. But solar geoengineering can't get you out of the need to deal with CO2. Let me say a little bit about uncertainty and then wrap up. How am I doing for time?
You have about 20 minutes.
Okay, happy to take more questions. So I just gave you a talk with a bunch of climate model results, and I tried to sort of back off from them. I had lots of numbers that had, looked like they had uncertainty of a few percent, even though the uncertainty is bigger. In fact, there's deeper uncertainties here about how these technologies would work, how to assess them, and that's because there hasn't been much research effort. So there's been a kind of taboo. It's changing about research on this topic. So there's very, very little research on this. And I and others are arguing that there ought to be a lot more research, but that hasn't really happened yet. So I want to say just something about putting that in context. So I think the central issues of uncertainty are what's missing, what's not being studied. And another issue is that I think is actually quite quickly resolvable is about groupthink. So right now, a relatively small group of researchers, it's not as small as it was, it's now global and not nothing, but still a comparatively small group of researchers have really looked at this carefully. And I think it would actually be quite easy to have a much larger group look at it, because again, this is essentially applying existing broader knowledge in atmospheric science, atmospheric chemistry, applied aerospace engineering. And it wouldn't be hard to get a much larger group of people to look at this carefully. And my perspective is nobody should make any decisions at all about these technologies until there's been a much broader set of people looking at it very carefully. So that's the kind of groupthink aspect. But then you actually, if you want to make real progress, there's a bunch of actual research you need to do. And to give you some sense of the way I think about it, this is just for stratospheric solar geoengineering, and there's a bunch of other kinds. This is part of a sort of tree-based tool where I have layers and layers under this. I'll show you some of the layers. So under this improving predictions layer, there's a whole set of research where you could easily spend kind of $100 million a year, which might sound like a lot, but it really isn't on the scale of what we do for emissions or even what we do for climate research. And there's a whole bunch of research one could do to begin to understand better how these would work and how risk might be better quantified. That's just one example. Here's another example about understanding deployment. I'm not going to go into these in detail, but just to give you a sense that there's a sort of underlying set of research that could be done, and maybe to flag that there's in about a month, the U.S. federal government will actually OSTP, Office of Science Technology Policy, will release a formal research plan. It's not clear how detailed it will be. That tries to tries to outline what a U.S. Federal program of research might look like. So to give you a sense of that, there is the potential for more research. There is more research happening. I want to show you one last paper that kind of links to this economic way of thinking that I feel like is a good paper to show for this topic, which is what's the value of research? Because of course, people have different feelings about whether that research should happen. And there are people who really believe we shouldn't be doing research. There are thoughtful, serious people who really believe that research on this topic should not happen because it will inevitably be misused or inevitably be used to say, delay emissions cuts. And so it's really better to not know more. I obviously don't believe that, but it's a real point of view. And what we've tried to do in this paper is to think about quantifying the potential value of research and doing it with a simple value of information framework using a version of DICE that has a version of solar geoengineering and carbon removal in it. And the simplest version of this, I'm just going to show this slide and one more, is this following box that I find very useful in helping to think about the two sides of the coins around solar geoengineering. Of course, the coin really has more than two sides, but let me first give you just a two-sided version of this. So if you think that we've got our belief about whether solar geoengineering works or doesn't, of course, it's not actually binary, but it's useful to think about it that way. And we have reality of whether it works or fails. What I think almost everybody who thinks about this topic is sensibly worried about is overconfidence, as we're worried that we're going to think that it works, proceed to kind of make policy assuming that it works, and find that it really doesn't work. I think that's a completely valid risk. There's no question there's a possibility of that overconfidence. But I think in thinking about it, and the reason to draw this diagram is people often think only about overconfidence and don't think enough about the converse risk. And the converse risk is very real. So the converse risk is underconfidence. The converse risk is that we assume that solar geoengineering doesn't work, so we ignore it. And then we find out, say, in 2050, of course, it's not really binary. I'm just giving you this in a simple binary. We find out in 2050 that it really would have worked pretty well. Not perfectly, but that it would have allowed massive reductions in actual risks, like mortality risk from heat or risk to ecosystems. And then we sort of imagine our kids or grandkids looking back from 2050 or 2075 saying, wow, the biases of ignoring this meant that we lost the opportunity to really save millions of lives. I think that's a valid risk as well. And I think the issue is how to think about these two risks. Obviously, the happy answer is that we correctly assess that it doesn't work and it actually doesn't, or we correctly assess that it works and it doesn't. But I think the key issue is that if you think about overconfidence, which is, I think, in a healthy way, but everybody thinks about first, don't forget that there really is an issue of underconfidence, of underusing technologies that really could potentially have reduced risk in material ways. So using the DICE framework, which you can think of lots of critiques of, we actually quantified that this is the values in trillions. And now I'm not making it binary anymore, but this is, and I won't go into how, but this angle here is a proxy for how well solar geoengineering works. So this means it really doesn't work very well. This means it works very well. And then we've done this in a continuous way instead of just a binary. Lots of ways you can pick apart this number. But one thing that should give you some confidence is the number we get to is of similar scale to the number we get to for the value of information of reducing uncertainty about climate sensitivity, which kind of makes sense. One of the central things about planning under uncertainty for climate is we don't know how much the climate is going to change for a given amount of CO2 emissions. That's what we call the climate sensitivity. And the point is, knowing more about how well solar geoengineering works or doesn't has got a value that's kind of the same order as the value of reducing climate sensitivity and uncertainty. And that value is really big. And give you a sense of what the actual number is, cutting it in half by 2030 is sort of worth 4 trillion-ish. And to me, that's a pretty strong argument that it does make sense to spend kind of 100 million class money a year to really work on reducing the uncertainties. Of course, we might spend the money on research and not reduce uncertainty. That's the reality of research, but it's still an argument for doing the research. So thank you very much. Happy to take questions.
When you, I can just also speak loudly.
It's hard for the Zoom.
Okay.
Thank you.
When you talk about the moral hazard argument that people make that bad actors might misuse this as a way to say we don't need to reduce or decarbonize, are you aware of any examples of emitters pointing to this research or to the existence of solar geoengineering as justification for that?
Yeah, there's little bits, but nothing very obvious. So there's some early research from the American Enterprise Institute that you could argue point in that direction. But strangely enough, there's actually been some strong commentators on the political right arguing against solar geoengineering that sort of is contrary to your model for how it might work. So I think the answer is not yet much. But I think it's a reasonable expectation. I believe self-interest explains a lot of behavior. So I do expect that if solar geoengineering really becomes more visible, and more of a real prospect, that some forces in our society that want to slow down emissions cuts for their reasons will choose to say that it works even better than the evidence suggests in order to try and make that argument. I think that many people just say that and don't think about where the real trade-offs are. And I think what I've never seen, which you go ahead and write the paper, is a paper that deals seriously with a kind of median voter theory. So the way I think about this problem is that people, I mean, obviously the world isn't quite this simple, but if you think of this as kind of the fossil right versus the green progressives, the fossil right is going to strongly argue for slower emissions cuts kind of no matter what. And the green progressives are going to argue for faster emission cuts kind of no matter what. And neither of their opinions will be changed by the presence of solar geoengineering. It's not like the green left is, if solar geoengineering is part of the thing, is going to say, well, we don't need emissions cuts. Of course, they'll still say, and I consider myself mostly part of that group, that we should do emissions cuts. The way this will matter is how it changes median voters who don't care very much about this one way or the other, about this meaning climate change, and how it changes their risk perceptions and therefore their voting behavior and therefore political outcomes. And nobody, to my knowledge, has ever sort of seriously started to think about that. Lots of hands. How should I do this? Okay, yeah, so why don't you guys sort of work your way back on the mic? Yeah.
Yeah, so I think it makes sense that mortality was your first sort of frame of reference for quantifying things. I can see how higher pollution leads to less productive workforces, and then obviously other heat effects on ecosystems.
Yeah.
What are the next measures that you're looking to incorporate into this modeling?
I'm not sure. I have a separate paper I'm working on that tries to compare the risks of carbon removal and solar geoengineering, and I'm trying to think about how to compare land footprint. So I think we tend to talk climate is the environmental thing everybody talks about now, but I don't, I think one shouldn't forget all the other ways that humanity damages the natural world through kind of appropriating land from nature. And I think some of the ways that we would do carbon removal or mitigation have environmental consequences through land use. And you can sort of think about this exacerbated moderated solar geoengineering thing, which there actually are numbers for, as an impact on nature, in the sense that if you take a kind of real ecocentric point of view, any place that you've exacerbated it is worse off. And so you can ask what fraction of the world is that, and compare it to what fraction of the world is made worse off because we're, some technologies used for carbon removal or mitigation. So I'm kind of fooling around with that comparison, but it's pretty, it's less tight and easily defensible than this.
So there's a high value of information that you calculated. What are the parameters that have the highest value of information in your analysis? And relatedly, how are you doing on experiments like small scale, actually flying planes and doing small scale experiments?
So we just did this in the DICE format where we just look at an overall uncertainty, the simple metric of how well solar geo works. And then we, of course, have to symmetrically reduce the uncertainty because you can't assume it's getting better or worse. That was that paper number. But as to the actual where we think the big uncertainties are, I would say that's where the research community does not have a formal, well-articulated list of the things that are the most important pieces of research to do to reduce overall uncertainty. And I think if we inch towards a more coordinated national program, that's something the community ought to do. One part of that is doing outdoor research, and there are outdoor experiments on marine cloud brightening that are happening off the coast of Australia. We've tried to do an outdoor stratospheric experiment that so far hasn't happened, but I think probably will happen. But it's important to say these are little experiments that like incrementally reduce some scientific uncertainties, but they're not tests of whether solar geoengineering works or not. They're, to me, from a scientific point of view, kind of a continuum with other things we do that are modeling or laboratory work, which has happened, or other kinds of experiments which are understanding relevant parts of say, stratospheric chemistry, but without actually releasing any new things. So there are experiments that happened in the kind of group associated with mine this summer, flying in the stratosphere that weren't releasing anything new, but they were learning things about stratospheric aerosols that are relevant to this problem.
Hey, Professor Keith. It's Melissa. So my question, so on the last slide with the 4.5 trillion, I very recently learned about the concept of the value of a statistical life. So it's really cool to see it pop up everywhere. I'm curious when you value that damage, for whom is this valued and for whose risk reduction is this valued? When I think about the whole world and the way this technology would be adopted in that global way.
So that calculation was from the DICE model, which adopts the point of view of a unitary global decision maker who's a utilitarian. And obviously that is very obviously not the world that we actually live in. But it is, I think, a crude way to calibrate it. I mean, maybe related to that is a conversation Tony and I have been having about Tony's reaction to the economist is, why am I dealing with Ys? Why am I not turning it all into money? Is that a fair characterization of what you said, Tony? So my answer is that well, I won't even give the I think there are good reasons to think about lives because we do have these direct estimates and it matters. But I mean, I go on for a long time. A couple kind of self-critiques. One is I just showed you total mortality, but in fact, when you look at mortality, it's better to look at measures of years of life lost than mortality, because if the people are dying just before they would have died anyway, if there's old people dying, that's, I think, of less consequence. And actually, we do have those numbers are underlined there in our paper, and it wouldn't be hard to do a version of this that was in perhaps even disability adjusted life years, but certainly in just life expectancy. So I think that's actually better. We do look a lot. I mean, I didn't go much into it at the distribution of those benefits. And I think one of the things that I take as a most serious ethical reason to take solar geoengineering seriously is it does seem that the benefits, both of reduced mortality and of increased economic growth, the two biggest benefits of solar geoengineering, go most in general to the poorest. So there's a slide that I didn't show you yet that we've built for the paper that shows the poorest 3 deciles or so have by far the biggest benefit in terms of reduced mortality. And I think that's a kind of important reason to take it seriously. And while there's lots of little methodological things to complain about the paper, I think that's likely to be a very robust result because it's just tied to the thing that we really know well, which is incremental degree of temperature is worse in places that are hot, and in general, the hotter places are poorer. Obviously, there are Singapore and other exceptions, but that means that when you reverse that warming, you should expect that effect that the benefit is more for the poorer.
One of the challenges that the Carnegie Climate Governance Group has been looking at is SRM tends to be relatively affordable, which means you could actually have a small group of nations, a single small nation, a corporation, or even a single billionaire sort of go out and start doing some of this stuff. How are you thinking about some of the governance challenges of that? And maybe it's not a multilateral agreement, but it's a unilateral actor just sort of going out on their own, trying some of this technology.
So that's obviously not part of this paper, but many people here have thought about it for a long time. I think we need some kind of restraint on unilateral action. So the C2G effort is moving towards a UNGA resolution that would do something about that. Ted Parson and I had a proposal in a Science Policy Forum article about a good chunk of a decade ago now that proposed a global moratorium where we had explicit thresholds of what constituted deployment. And so I think that some version of that is important. And I think it's important to allow a more reasoned conversation about how to treat these technologies, to have some restraint on unilateral action. I actually think that the sort of extreme versions of that you said of sort of 1 billion, I think there's a bunch of reasons we really think that out. It's really not very plausible, but I still think there is some underlying potential for at least minilateral action that is plausible. And I think we do need to think seriously about how to regulate that. Absolutely. So I don't have any specific answer. There's a whole host of research around how you tie decisions around implementation to mitigation decisions, where you'd sort of have a procedure that gave more weight to countries that were putting more effort into cutting emissions, and that would kind of be a counterpoint to the moral hazard concern. Lots of stuff.
Thanks for the talk. Where do you think solar geoengineering fits in the climate solution scenario? In a sense, like you gave where it fits in the causality chain, but in practice, where do you see it? Like, is it gonna be something temporary until we get carbon sequestration at scale? Like, where does it fit? Even in timeline, maybe.
So that's another talk. You may have seen me give it another time, Carlo, I'm not sure. But I think my view is that if it fits at all, it actually should happen early, because you want to ramp it up and have the peak of the amount of solar geoengineering at about the time where you have peak concentrations, and then ramp it down. So that if you imagine that you're gradually decarbonizing the economy to zero, and that you do carbon removal, so that the combination of carbon removal and decarbonization produces some carbon dioxide concentration peak and then gradual reduction, that on the tail end of that, you obviously stop solar geoengineering. If you've really reduced the amount of CO2 in the air, then you stop solar geo. But that if you want to do solar geo as an additional supplemental risk reduction thing, it needs to be, it's utilitarian rational to center that peak, to center it roughly on the peak. And that means, and this is really different from how most people think, that means it actually might make sense to start solar geoengineering well before you started really large scale carbon removal, because large scale carbon removal, I believe, mostly should start once we're done a good chunk of the total mitigation.
Hi, David.
Hi there.
So I'm struck how quickly the whole climate debate is shifting on both sides of the Atlantic, the public debate about it. And I'm wondering, to what extent do you see that affecting the solar geoengineering discussion and the policymaking around this?
It's very hard to judge. It feels like it's changing, but it's hard, feelings, it's hard to be objective about how quickly it's changing. As some of you know, there's a new freestanding global commission called the Overshoot Commission that is by far the highest level political effort to examine these things. And the Overshoot Commission is roughly constructed to, of course, agree that cutting emissions is the most important thing, but to look at the governance challenges of things beyond cutting emissions, which means carbon removal, solar geo, and adaptation. And that commission has had 2 meetings, and it's got I think 4x heads of state, and a really kind of wonderful set of people with a lot of leaders from the developing world. And I'm a senior advisor to the secretary of that commission. Who knows what it will end up doing, but at least it is the most serious, by quite a long way, political conversation about the governance of these technologies. And I think that, I hope that the commission will deal with the interaction of them. I think a lot of the commission is not going to, I don't think it's going to assess the specific details. That's not the job of that group. But I hope it could say something about the interrelationship of these things. And that really hasn't been said by a kind of competent political body before. Sure.
Yeah, just building on that, I guess I was wondering whether you could say a little bit about how solar geo fits into the overshoot debate within the Paris Agreement framework, to what extent, because it's not really, specified whether overshoot is an option or not within the Paris framework. And so I was not aware of the Overshoot Commission. And so I was wondering whether you could comment on that.
That's a great ending one. So is an interesting place where I and one of the strongest opponents of research on this completely agree, right? Pierre Humbert and I agree completely. So there's a very naive version of the argument that says, well, we've committed ourselves to keeping temperatures below 1.5, and solar geoengineering is a way to keep temperatures below 1.5. So maybe we've actually mandated solar geoengineering. I think that's just a crazy read. I mean, the answer is solar geoengineering was not part of the negotiations in Paris, and to claim that that's now a kind of post facto mandate for doing it is I think, outrageous. And moreover, there isn't actually scientific evidence there's some sharp threshold 1.5. 1.5 is a political target for political reasons. So my view is we simply don't have any agreement about how solar geoengineering fits or doesn't, and there's some people who think it should never be involved. My view is is that because there really aren't sharp thresholds in climate damages, it makes most sense to think about solar geoengineering as a supplemental risk reduction. And fundamentally, maybe I'll end here, I think that people always want to think about the interaction of solar geoengineering and carbon and how much mitigation we're doing, and it makes sense to think about that. But I think in some ways, as a public policy decision, they're less correlated than you might think. At some level, basic decision analysis says we think about the benefits and risks of something that we do. So solar geoengineering will have a bunch of risks and will have a bunch of benefits, and the ratio of those benefits to risks may not depend that strongly on where we are in emissions mitigation. They might largely stand on their own. I think that's my guess of how it plays out.
Okay, before we wrap up, a quick reminder, we'll meet again at noon on Monday, November 7th in this room, and on Zoom. We'll be hosting Brian Prest of Resources for the Future for his talk, The Climate Economics of Oil and Gas Production on Federal Lands, from Campaign Promises to the Inflation Reduction Act. And finally, please join me in thanking David Keith for his talk today. Thank you, David.